Hi, everybody. My name is Lily. I am a senior product manager for technology at Tencent Games. And today I'm honored to be invited here to tell you guys about a very exciting projects we have. So at the technology department in Tencent, over the last 20 years, our mandate has been creating technology that will support our wider portfolio studios within China and overseas. And today, this year we have done a very exciting one with Honor of the Kings, the Chinese version, and with Qualcomm. As you can see in the title, today we will be focusing more on the AI ASR and especially how we brought that on device. And then I'm going to hand over to Jane to tell you a little bit about the history of our collaboration.
Thank you, Matthew. Thank you, Lily. So here, I'd like to welcome everybody to the talk. And so my name is Jane. I'm the global lead for the Qualcomm game developer technology. I just give you a bit background of how this collaboration started and where we are heading. So the collaboration with Tencent GVoice has been a long, ongoing journey. So we started exploring opportunities as far back to 2018, and then later in 2020, we have finally found the solid ground to collaborate together. And further onto 2022, we have experimented like the first time with on-device AI denoiser and ASR. So as we all know, that technology is fun, but it's just gonna be like, we need to find a real scenario for testing. That's why 2 years later, together with GVoice, we started the collaboration with the Honor of Kings China server to explore this GVoice technology on device and testing new territories together. So I'll hand it back to Lily to introduce more the technical background.
Thank you, Jane. All right, to tell you guys a little bit about what you can expect today. So we will be looking at the reality of our challenge, the building blocks that we had to play with, and the path leading towards on-device AI. Before I start, I would like to add a little bit of caveat. So what I'm going to tell you guys is not that how we solved ASR forever for everything. It's merely that we're going to look at a very specific case and how we solved it with the challenges that were presented towards us. So before we start, let me introduce you guys a little bit to GVoice and who we are. So GVoice is Tencent GameVoice. We are the primary gaming VoIP solution within Tencent. We have been doing this over the last 20 years, especially with Honor of Kings. We've been doing that for about 10 years and various other titles within Tencent. Our technology currently sustains roughly about 300 million DAU worldwide, and we refine it over the 500 projects that we have dealt with and that have used GVoice. So we do pride ourselves to being very ultra low latency. Even in weak network scenarios, we do have a very strong AI denoiser build, and we support cross-platforms. And obviously, additional to that, we also come with general VoIP features that people need, such as like voice chat, multi-channel chat, and proximity chat, text-to-speech, speech-to-text, the whole shebang. So for us, working with Honor of Kings, especially in China, has been a long-standing thing. So Honor of Kings came out in 2015 by Timmy Studios. And ever since they brought in voice solution, we have been walking this path with them. It is, until today, the most played MOBA game in the world. I think at our 10th anniversary, we have measured up to 139 million DAU, which is a crazy number if you think about it. So Honor of a King, as I mentioned, is a 5v5 mobile MOBA. So this game presented itself with a very complicated scenario for voice and voice communication demand. So what does that mean? The game is highly collaborative, so we really need players to talk to each other in order to succeed. For anyone among you who have played a MOBA, you understand that maybe the success is just within seconds, and you really need to make sure your team member understands you. And given that it's also a mobile game, which means people play on the road, people play anywhere they want, it is very sensitive to latency. And of course, you know, especially in China, also overseas here, when we play a mobile game, we don't do it from home, from the couch, in a very controlled environment where you have, you know, quiet, you know exactly what people are gonna hear. People do it on the road, on the train, in restaurants, in public spaces, and together with the game's sound effect, together with 4 other members speaking beyond yourself, and background noises, we're presented with this perfect scenario of challenges to say, let's push the technology a little bit further. So that is basically what we're looking at in this scenario with Honor of Kings Chinese version. Before we dive into the AI ASR on device, let me talk about automatic speech recognition a little bit. I assume that most people already know what this is. In case you do, please bear with me. Let me just walk you really quickly about what it is. So essentially what ASR means is the process of bringing whatever I'm talking, for example, onto a text format. So the microphone would pick up the input. It will run through our enhancement program, so we can determine what is actually spoken. We have better audio output, and then it will run through our recognition system, where this is usually changed to text. So the text is one way of the output. So for example, what happens a lot these days is accessibility. You know, you have speech to text, which is important for those who cannot hear. For example, they're on the road, or they're playing in a quiet environment and his family is sleeping. So com caption is a very important thing in ASR. Another thing is moderation, obviously. When someone says something, we can recognize it, we can determine if anything is wrong with it. And in the last couple of years, we have also been working with directly using the output for AI prompt. So that is not even like putting it into text or chat box, it directly prompts AI in the background. And here I have a video for you guys to see how it actually works.
中路请求集合，一起集合推塔。
再来一次，人力上任，我升级啦！
等等我，马上到。等我集合打团。优先处理输出。
Right, let's talk about the subject that why we're here. So moving from cloud to device, given that we have experimented with AI for quite a while within GVoice, for us this is the logical next step, especially that we have been doing so much in mobile gaming. What does that mean, moving from cloud to device? It really means for us to move to an NPU. Instead of traditionally using the GPU or CPU to process things, we have to do it in a way that can actually run on a phone. So traditionally, cloud ASR works really well for us. We run a bigger model. We can update a lot more frequently. We can scale, but it also means it comes with the network round trip, which is an added latency. As I mentioned in the earlier slide, for Honor of Kings, the version, it is incredibly latency sensitive. So that was something that people were actively looking at solving. So putting it onto device, we basically cut away the network round trip. We can work with a lot more consistency. We can work with a lot more responsiveness. Here, another caveat. We're not saying we have solved it for everyone, for everything. It's really in this scenario with HOK, the Chinese version, the trade-off was worth it for us. So let me talk about a little bit more how we get there. Let's do reality check. What does this mean? We needed to have a technology that can detect and remove interference, be it noise or other people or microphone variations. We need to actually identify who is speaking. You know, obviously here, you know, we already have a directional mic, they will pick me up. But then in real life, you have so many other people around you, right? And we actually need to recognize the correct language. So the model that we're using here, we have trained it for Chinese. But for the Chinese speakers among you guys, you all understand Chinese is not one single language that's spoken exactly the same way. It comes with variety of dialects and regional slang. So we have to train a lot of variety of it. And additionally, we have to make sure latency is still good for the game. We have to maintain the memory footprint, and we have to stay within the battery and thermal budget. So this is the reality that we're dealing with. What did we actually do? In hindsight, it sounds like we know exactly what we were doing, but obviously in the process, it's a long way. We did a lot of try and error. but this is why I'm here to tell you guys. We roughly can group it into 4 things that we have done. We will teach the model, we will train it, we will distill it, and we will compress it so it can actually be on device. So let me share more stuff. The first thing that we did is the in-domain optimization. So this generally is the process where we turn generic talking into HOK-specific speech. We trained with a natural language model, so it will detect what people are actually saying, and then slowly on top of that, we have added data from the H2OK realm, which means like this is gameplay jargons, this is whatever slang is currently in trendy, names and heroes and things that will happen in the game. So the model will recognize what is a normal, things that we will be saying in real life and what is actually very in-game specific. And these data that we actually use were provided to us by the game team, and these are synthetic or semi-supervised. And this way that we can train a very specific model that is just for the game. We managed to control the parameters without relying on manual labeling. We managed to keep it small because we only needed to train it in the very specific scenario. And the second thing that we did is adapting the training network. So what we did here is, this is really the part where we talk about the enhancement and the audio cleaning. Usually people understand, like the audio comes in, it needs to get enhanced, so it gets cleaned. But the cleaned output might sound really good, but it might actually lose a lot of information that you need for the ASR. What we have done is we have linked our own enhancement model with our ASR while feeding it data for the ASR. So what they recognize, they will take into consideration how it was cleaned, what was the device used to getting it. Just in case we have artifacts, it can still recognize pretty well. I'm sorry, somebody's messaging you on this PC. Apologies. So this, with all these things done together, our enhancement model, our ASR, and they're all linked together where we get fed in all the different data, we managed to stay quite robust across various microphone input. And this is, one of the numbers that we have measured roughly is that we can, reduce the character error rate by roughly 13%, which is quite good in our scenario. And the next one is really about the model itself. AI models can become very big. If they run on the cloud, that is actually acceptable for us. But to put it really on device, we need to keep the size measurable, we keep the size small enough to fit on the device, while stay within the memory footprints that we've been given. So we did 2 things mostly here. The number one is how we distilled a large model into a small model. So here we used the very traditional, like a teacher-student scenario. We had a bigger model that runs better, is faster. Well, not necessarily faster, but it's better and can process more and give us more accurate outcome. And then we have a student model that will emulate that behavior. And this way, we actually don't have to go through all the processing while having roughly measurable good outcome that was acceptable in our scenario. The second thing that what we did here is to distill a non-streaming model into a streaming model. What does this mean, really? We had to keep the model size small enough. So non-streaming model usually is when I finished what I said, right? And it will take the entire context and go through it again, understanding where to break the line, where to put the punctuation, and am I using the correct character? Given that we have trained it in Chinese, the Chinese language is built in a way that it sounds the same, but it's written differently, and they will have different meanings. In normal speech pattern, we would determine a lot of that by context. But if you're just dictating in a way into the mic and then expecting text to show up on screen, it might actually get it wrong. A streaming model will be just directly text output, which will sacrifice so much accuracy in our scenario. So what we did here is we actually trained this non-streaming model to give out the correct and good output, and then have it guide a chunk-based streaming model. So we still get a certain amount of accuracy that works in our scenario. As I mentioned in the first part, we did the in-domain optimization, so we understand what type of speech will be said within the gaming scenario, right? So together, we managed to get it into a way that is actually accurate enough for us, it is small enough for us, and it doesn't really, blow the memory footprint that we have been given. So together, roughly here, with the distillation from a large to a small model, we managed to reduce our character error rate by roughly 10% in comparison to just training a smaller student model from scratch. And on the distillation part, from the non-streaming to the streaming one, we roughly reduced it by an additional 7% in comparison. So these two things were very important for us to get the model small while maintaining a certain amount of accuracies, and while staying within the real-time constraints. And the last part is really about how we actually manage to bring this onto the device, which is compression. And this is the part where Snapdragon really supported us with their NPU. So the first thing that we did here is to use a 4-bit dynamic aware weight quantization. So we pushed the weight into the int4 and then kept the activation in 8, so we actually get more accuracies this way. This kind of format is built with the NPU, so it just runs more efficiently, it moves less data around, and therefore runs the heavy compute faster and uses less power. The key here for us is to avoid the native PTQ accuracy collapse. And with our dynamic approach, the CR got a lot smaller, it's roughly around 4%, compared to the 10+ % when we're just using a pure PTQ method. The second thing is downsampling. One of the major ASR costs comes from the times per step, right? So by reducing the frames, we managed to save up on the compute. And this is also by design, how we did it. And in this way, basically, instead of doing every 4 frame, we did every 8 frame, which means we saved about 30% compute, which means it moves less stuff, it's faster, it's better, the phone doesn't get hot, which is a no-go for our mobile gaming scenario. And the last thing that we did here is a 2-stage decoding. So number 1 is we stream fast for the output, and number 2 is we go back and correct anything that isn't accurate. Because player in the actual real gaming scenario, they need to communicate whatever they need to say as fast as they can, and also receive something back from players. Here, the trade-off really is accuracy versus responsiveness. And these are the things that people can play within their own development is what do I want to have more? What is acceptable? We're not saying that there is a golden formula for certain things. It's really for each development team to figure out what works for them, as we're continuously working with the game team to figure out what is the sweet spot for us. There are some other numbers I would like to share that my engineering team, who unfortunately cannot be here today, are very proud of. Overall, we managed to keep it with under 100 megabyte runtime memory. The model scale, the smallest one that we have created, roughly sits around 90 megabyte. However, though, we did try a bunch of different models of different sizes, and then again, this is coming back to with the game team to discuss what is the good trade-off. Accuracy is comparable between cloud and on-device at the end of the day. There are things that we can measure that would definitely run better, but again, trade-offs, no network latency, the responsiveness, for us, it is a good win. So on-device, roughly, we're sitting around 0.92 character error rate, which is roughly at 1%. Again, we have a roadmap to improve this, but overall, right now, it is a model that works. And then lastly, most importantly, is that it's just faster. 55% faster inference. This is measured by the character on screen. In a mobile gaming scenario, this is an incredible good outcome for us. Coming to the end, at the takeaway, ASR high level is not very complicated. So you have mic input, you have enhancement, you have recognition, and you have output. For us here, bringing our AI ASR model on device, Snapdragon really helped us a lot in the recognition part. They did the heavy lifting there. And then with how we constructed the model, the teaching, the training, and the distillation happened within offline. We made the adjustments so it will fit on the device. And then distillation, again, is where Snapdragon really enabled us to make this jump. And now, that is about what I can share with you guys tonight, or today. And then I'll hand over to Jane to tell you guys a little bit more about Snapdragon and the AI stack.
Thank you, Lily. So that has been quite amazing to show you like how ASR solution can run so well on Qualcomm platform. So you might, as a developer, wonder, okay, so I have my own on-device solution, and how can I deploy that on Qualcomm platform? So here are some tips and some resources I'd like to share. First of all, I'd like to go over the all-stack enablement. We are not just running a model on NPU. We are using the Qualcomm AI engine direct and the QNN to actually schedule the workload across the right compute blocks. And also, in practice, the NPU takes the heavy inferencing. The core recognition work side, actually, the core recognition work actually sits on the NPU. Besides that, we also have the CPU that handles the speech pipeline. And on top of that, we have the HVX, actually that help with the acceleration under the mobile power limit. And now, let's go over the Qualcomm AI stack. So as a Qualcomm developer platform, we provide developers with all kinds of SDKs and tooling. As you can see at the bottom, we have our hardware, and then we provide all sorts of Game AI SDK. Just want to shout out that we announced the Game AI SDK today at this conference. And then you can also see the tooling side. We have the Gen AI extension, the AI Mat, and all kinds of our quantization tools to actually deploy your solution on Qualcomm platforms. And last but least, you can scan the QR code here. So we provide you all kinds of links to our GitHub page and to where you can download the Game AI SDK to actually enable your on-device deployment. Okay, so to wrap up today's discussion, if you have any questions or any feedback, feel free to communicate with us through Discord, and we're happy to answer any questions you have. And then thank you all for coming to today's talk. Thank you.